Okay, thanks. So this next session, the goal of this session is to highlight different types of buildings and built environments with the goal of comparing and contrasting and looking for commonalities or not between different types of sort of classical buildings. And so first we're going to get started hearing from Tiina Reponen about homes.
Okay, good afternoon, everyone. As Rachel said, I'm going to be talking about microorganisms in homes and mostly about fungi, but also a little bit of bacteria. And when we were kind of thinking about this session, I was asked to focus on two main questions. What is different in homes compared to the two other environments that we are talking here, the hospitals and the International Space Station? And then also talk about a little bit about the health effects. So when thinking about what do we know about homes, and I know a little bit about hospitals. I don't have experience in the from the International Space Station, but I think that is kind of on the other extreme environment there. But what do we know, what is different in homes? I think that there's a prominent effect of outdoor environment on indoor fungi, like we've already heard, and more prominent than in the other environments. Second, there are pets, presence of pets, cats and dogs that affect the microbes in homes. The sources of humidity, there could be more sources of humidity than the other environments, cooking, laundry, and Patricia mentioned dishwashing, so I wanted to add that here on the list. And then also building materials. There tends to be more wood-based materials, textiles in homes, which are more prone to mold contamination than other types of materials. So I was going to give you a few examples about this specifically about the effect of outdoor environment, presence of pets and so on, but I'm going to go this relatively quickly because Shelley actually showed already some of similar types of results. Just to want to point out, I kind of just for the fun of it went back, all the way back, digged up old results that we published with my Finnish colleagues many years ago. And this one is based, the first few slides are based on cultivation analysis, air samples and cultivation analysis. In this one you can see we looked at seasonal variation of fungal spores and bacteria, both indoor and outdoor air. And we can go back to more the details if you are interested in this. I just want to make the conclusion that I had written before I saw Shelley's presentation. We already concluded then that outdoor environment affects indoor fungi, but not so much indoor bacteria. So it's nice to see that there are also the next generation sequencing new results are kind of confirming that. This one was a different study where we had three experimental apartment complexes. Each one of them had 6 apartments, people living there, and they were exactly otherwise similar structures, same building materials and so on, but they had different ventilation system. On the left-hand side is mechanical exhaust and middle natural ventilation, and then on the right-hand side mechanical exhaust and supply. Just again going to the conclusion from here, what we learned from this one, that if we have a filtration that was in the mechanical supply units, where the filtration of supply air reduces the outdoor-indoor transport of fungi. But it did not have effect of bacteria because the bacteria were more affected by the occupation than the outdoor environment. And then last of the old results is when we had a set of experiments where we looked at how some normal daily activities affect fungal spore concentrations, and we did all kind of things that people do in their homes, cleaning, changing sheets, opening a moldy jar. And this one was an experiment where the family owned a cat and dog, and the cat and dog came in during the experiment. And you can see concentration skyrocketed, 10 times increase, and then half an hour later, it actually had decreased almost to background. So this kind of gives us actually two lessons. So pets do have an effect of indoor fungal concentration. In this, we did not differentiate cats and dogs in this. They both came at the same time. And the other one is the very, very high temporal variation in indoor air, especially in the air concentrations. So these were cultivation-based, and then this one is a kind of a very simple summary of later studies in Cincinnati when we used the next generation sequencing and looked at how the diversity of bacteria and fungi is affected by different kind of home characteristics. And here you can see that for this set of studies, the dog affected the bacterial diversity, and then for fungi, diversity was affected by relative humidity, age of the home, and then moldiness of the home. So again, these kind of supporting what Shelley showed, and also I think Rachel Adams has also looked at the things that affect the diversity of the composition of indoor microorganisms. So all this is very nice. It's good that we have from different studies similar kind of conclusions. And but then, can we use this to decide the interventions? Do we really want to get rid of dogs to get the fungal spore concentrations lower and reduce the diversity of bacteria? So the real question is, how are the microbial exposures affecting health? And that should be the basis on deciding how do we want to intervene. So that brings me to the second set of my talk is to looking at the health effects, and I'm going to be just giving you some highlights of the study, the longitudinal birth cohort study that we have done in Cincinnati Childhood Allergy and Air Pollution Study, CCAPS. And this was a longitudinal birth cohort study that looked at role of traffic pollution and bioaerosols. So traffic pollution coming mainly from outdoors, bioaerosols coming both from outdoors and indoors. And how does that affect children's allergy and asthma? And that's our logo. The voice is gone. We used to have a truck sound coming with that. So my background is exposure assessment, but I've collaborated with medical doctors and epidemiologists, and I'm going to just briefly summarize how we assess the microbial exposures and not go into deeper details on the other aspect of the study. We did both qualitative assessment, meaning we looked at what can we observe as qualitatively, if I can find looking at water damage, visible mold, moldy odor. So the study team went to each and every home and looked at the signs of these qualitative signs. We did quantitative assessment for endotoxin and beta-glucan. We analyzed dust samples, then we analyzed air samples in 2 different size range, from inhalable size range and PM1. And this was, the PM1 was looking at the fragment size range, and I'll come back to that later in the slides. We did total spore counting from air samples, collected sample on filter and did microscopic counting from that. And then we did a quantitative PCR analysis of 36 different fungal species, and this is the ERMI, Environmental Relative Moldiness Index, that Patricia mentioned shortly in her talk. And then also we did quantitative PCR assay for streptomyces, and this is belongs to actinomyces. So you can see that this qualitative assessment was mostly focused on fungal components, but we also had endotoxin and streptomyces to represent bacteria. Okay, so here is the very first result that really highlighted for us that we really need to look at the mold exposure as thoroughly as we were looking at the traffic exposure. We looked at, here is a risk of, okay, this is going in and out, but on the y-axis is recurrent wheezing, risk for recurrent wheezing, and then the different factors that affected the wheezing when looking at exposure at age 1 and wheezing at age 1. And we found the commonly known risk factors at upper respiratory condition, lower respiratory condition, more than 2 siblings, African American race, parental asthma, mother smoking were risk factors for wheezing. But visible mold was also risk factor, almost as high risk factor as mother smoking. In this particular study, we did not see endotoxin affecting. It's kind of around 1, risk ratio is about 1. But then beta-glucan, interestingly, had an inverse association. And I'll come back to this inverse association, but let's talk a little bit about this visible mold. So what we learned here, that H1 exposure was important. If the child had visible mold in their home at age 1, they were 4 times more likely to have wheezing at age 1. And this association held up at age 3 wheezing also. When we looked at age 1, mold was still associated at age 3 with wheezing in the infants. So then we went back to these homes later at age 7, and looking at the exposures at age 1 and age 7, and then asthma at age 7, because then everybody was assessed for asthma, looking at did they develop asthma or not. And the only factor that among these dust beta-glucan, dust endotoxin, PCR-based assay of mold and the visible mold, the only one that was associated with asthma at age 7 was the PCR-based assayed mold, ERMI index. If the child had high, if the home had high ERMI index in the home at age 1, the child was more likely to have asthma at age 7. Noticeable that none of these year 7 exposures were affecting asthma. They were not significant. And also that visible mold, so age 1 visible mold, was not anymore affecting the asthma at age 7. The visible mold had affected wheezing at age 1, increased the risk of wheezing, age 1 and 3, but not anymore asthma. And then, so one lesson learned here is timing of mold exposure matters. And also, how do we measure the exposure matters, what we might be finding. Here is just a multivariate analysis where we adjusted the risk, and you can see here the ERMI still remains significant. In the adjusted model, we have parental asthma again remaining as a significant risk factor. Sensitization to house dust mite is also a risk factor, but interestingly here you can see air conditioning is here, which is the odds ratio is less than 1, which means that it is a protective effect. If there was air conditioning in the home at age 1, the child was less likely to have asthma at age 7. So here would be one target for intervention, which is based on health data. So then let's look at the beta-glucan. I promised that I'll come back to the beta-glucan. Here is beta-glucan again. In y-axis there is prevalence rates of recurrent wheezing, and in x-axis there are, on the left-hand side is a concentration microgram per gram of dust, and the right-hand side microgram per square meter of floor area, beta-glucan concentration. What we can see here, that if with the low exposures, when the beta-glucan concentration increases, the risk of wheezing increases. And then there is a turning point beyond what then, if the concentration increases, the risk of wheezing actually decreases. So we see that protective effect here with higher concentrations. And first we kind of didn't believe this, but then when digging up the literature, we found that there was similar association has been shown for house dust mite also, this upside down U-shaped curve. So what was the lesson learned here is concentration matters. And then the second lesson is microbial exposures can also be protective. So this is not necessarily harmful. Some types of exposures could be protective. This one is not actually from our study. This is from Jordan Peccia and Mark Mendel and Karen Dannemiller. They looked at archived dust samples from an asthma cohort here in California, and they showed that if the home had low diversity, or let's say they had like asthma cases and controls, so the asthma cases, in those homes the diversity was lower than in the controls. So asthma cases, the diversity of fungi was lower. So this kind of brings this issue about the diversity also matters. It may affect the health. And then size distribution. This one was an experiment where we looked at release of fungal particles from moldy surfaces. And we were kind of initially targeting the spore size range, and you can see Aspergillus versicolor, very nice peak for spore. So in y-axis is concentration and x-axis size, so 2 micrometers was the peak for Aspergillus versicolor. But then surprisingly we saw also a lot of smaller particles here in the less than 1 micrometer size range. And it was confirmed by microscopic analysis that these were not intact spores. And we did some immunoassay with fungal specific antibodies to show that at least some of these particles were from fungal origin. So this is Aspergillus versicolor. Then we had another example is Stachybotrys cartarum. Here you can see that this fungi doesn't typically release a lot of spores. We don't find that in the air very commonly, but then surprisingly we saw a lot of fragments. So now you could think if we had only focused on the spore size range and taken a sample only from spores, we would get a very different picture on the exposure than if we had also included the smaller size fraction below 1 micrometer. And I will show other study here from Korea, Seo et al. They used NIOSH developed two-stage sampler to differentiate beta-glucan in fragment size range, and they showed that the fragment concentration in homes of asthmatic children was higher than in non-asthmatic children. So then this lesson learned here is that particle size matters. We should also think about these fragments and how we could be able to measure those and include those in the analysis. And then the final result here is I want to now bring some of this traffic pollution, that this was actually the focus of the CAPS. This one shows, this set of figures shows the synergistic effect of traffic-related particles and endotoxins. So the bar chart here on the left shows children who had low endotoxin and then children who had high endotoxin. And then the darker one is low traffic pollution and the lighter one is high traffic pollution. So, and then the risk of recurrent wheezing at age 3 on the y-axis. So what we can see here that the group of children who had both high traffic pollution, exposure to high traffic pollution and a high endotoxin, they had way more wheezing than the other groups. And then when looking at the adjusted model, the risk was 6 times higher for those who had high in both categories than those that had low in both categories. So then the lesson learned here is other non-microbial exposures matter too. So we should not forget also to look at the mixed exposures. And then finally, my final slide, just to thinking about what might happen in the future. I don't have a crystal ball. This is just my educated guess. I don't think that the mold and dampness problems in buildings will go away. And there has been already a lot of talk about these energy efficient houses and sustainability. So we need to make sure we assure sufficient ventilation, especially in those spaces where there is humidity generated, so that we don't get mold and moisture problems. And we've also seen in the news increased flooding. So this is, of course, a big risk for mold. So this is the call for urban planners on try to build residential areas for areas that are not prone for flooding, and then maybe some also attention to the building materials, what kind of materials we are using in areas that might be flooded, so that using those that are less prone for microbial contamination. So that's all what I had. Thank you.
Okay, thanks, Tiina. Next up, we have Bubba Brooks talking about hospitals.